Good morning, class. Today we are in section 2.1.3. The title is How Steep Is It? And we're continuing our discussion of slope. So let's summarize where we were at yesterday. Yesterday in class, we had discovered that if we have a graph of a line, right, we should be able to read from that the slope. And sometimes it's going to be kind of a rough approximation, but when I zoom in on this line, it appears to me that this particular point and boy, it takes a while. And this particular point right here are both hitting these perfect horizontal and vertical lines that stretch back to the x and y axis. And in fact, if I look at these, I can see that this line is got a value of 12 for x. So maybe I should put a little line here. This is at 12, and this line is at 6. And over here, this is also at positive 12, and this is positive 17. But it turns out I actually don't need those numbers. Well, I do. It's always important to go back and check to make sure that the units on your x and y axis are are units that you understand. In this case, the units are each one of these squares is 1 by 1. So I can go ahead and identify both the change in y and the change in x. So the change in y and change of x, right, these values are always measured along these horizontal lines and vertical lines. So there's a vertical line, and this measures the change in the y value. And here is a horizontal line, and this measures the change in my x value. And when I look at these, I can see just by counting that it appears I'm going up 1, 2, 3, 4, 5 units. And it appears that I'm moving to the right 1, 2, 3, 4, 5, 6 units. So if I wanted to identify the slope of this line, I would just have to remember the definition of the slope, right? And it's this rate of change of the y variable divided by the rate of change in the x value. So in this case, my slope would be positive 5, 6. If I start at this initial point and I move up 5 units, 1, 2, 3, 4, 5, and move to the right 6 units, 1, 2, 3, 4, 5, 6 units, I land back on the line. It's possible that we could not really have a very clear grid and be able to identify such points, but if I know the coordinates of the points I'm dealing with, I can use the coordinates to determine the change in x and the change in y. So again, I'm still looking for vertical and horizontal lines. So right in here, I'm just going to sketch a right triangle that goes, that's a little low, goes right about here. And I can see that I've got this horizontal line that represents the change in my x value, and I've got this vertical line that represents the change in my y value. And I'm going to go ahead and identify my y variables. Y is at 7 and y goes down to 5. And my x starts at 5 and it goes up to 9. So if I was going to look at how much these change in terms of just positive distances, my x variable does change by 4 units, right? I'm going from 5 to 9, 5, 6, 7, 8, and 9. So the length of that segment is 4 units long, and my y variable goes from 7 and it goes down to 5. The length of this is 2 units long, but I am noticing that it is going downward. And I might do this, I might not, but I might look at, for example, taking this to be a point and this to be a point. I might go ahead and look at the difference in the x values for my denominator, and I might take the 9 and subtract the 5. And if I do that, I would do the same exact thing for the change in y in my numerator. And you'll notice that I started at this point with the 9 and I subtracted, right, I subtracted the 5. I would do the same thing here. I would start with the 5 and I would subtract the 7. So if I did that, I would have 5 minus 7. Now, an interesting thing happens. If you do that correctly and you notice, look at my numerator. 5 minus 7 is negative 2, and 9 minus 5 is 4. Okay, okay. That looks like this has a slope of, equivalent to that is negative 1/2. So if I go down 1 unit, I would go over 2 units, and I'd be back on the triangle. So that's one way to think about this. But if you just want to think about, what's just the length of this segment, you can call the length of the segment 2. You can call the length of this segment 4. And just pay attention to the fact that, this looks like it's decreasing from left to right. Therefore, I know it has to have a negative slope. But if you go ahead and look at the difference like this and plug these values into it, you're going to get the correct slope. Now, I'm reluctant to do this, but I think in the times that we're at, it's probably a better tool that I give this to you. So I want to discuss something that's, I changed my mind. I'm not going to do it today. We'll talk about this later. Let's move on. When we talk about slope, one of the things we can associate with it is the steepness of a line, or in this case, the steepness of a staircase. And these look great, perfectly modern, wonderful set of stairs. However, it does feel like they're a little bit steep to me. And I can see here that I've got this change in y, change in x, change in y, change in x. And I would say those are fairly steep, and there's not even a handrail there. So use caution, especially when you're coming down with a cup of coffee. So the steepness of a slope, right, is basically a measurement of how far away the slope value is from 0. And I say that because it's possible to have a very steep slope that's a very small number. And what I mean by that is you can have a slope of negative 20 over 3, right? That's pretty far away from the number 0, negative 20 over 3. But a bigger number than that is 2, right? 2 is bigger than negative 20 over 3, but negative 20 over 3 would be much steeper. And it's just because its rate of change is larger, even though it's in the negative direction. So I want us to consider a couple different graphs here. So here's 4 graphs. And when I visually look at it, to me, it appears almost without question that this is the steepest of the lines I'm looking at. But I want to go ahead and calculate the slope of each of these. So I'm going to call these lines A, line B. This is B right here. This is A, B. I'm going to call this one line C, and I'm going to call this line D. And what I want you to do is pause the video, and I would like for you to calculate the slope of each of those lines. A great tool to use would be like to screencast it, blow it up, and maybe get to a place where you can do a few markings on it. But go ahead and calculate the slope of each of those, and then we'll come back and discuss it. Please pause. So I've gone ahead and drawn several slope triangles and labeled them. And you can see it doesn't really matter how far I go horizontally or vertically, as long as I begin and end on the line and I can know the actual length of those segments. So line segment A, if I record it one way, right, my delta y is 3, the delta x is also 3, but it's also 1 or 1, right? So the slope of this line is just 1 unit over 1 unit. The slope of line B, I've got a delta y of 5 units, and I've got a delta x of 1 unit. So my slope here for B is 5 over 1, or 5. And then for C, I've got this uh, delta y of 2 over delta x of 4. So I can write it as 2 over 4, and which is also 1 over 2. So I can see that these are equivalent fractions. So the slope here is 1/2. Now the only line that is has a negative slope is d, and it turns out this is kind of a good example of why it can sometimes be difficult to calculate the slope just based on a picture. So I hope you got 1, 5, and 2 for A, B, and C. But I can do this and you can't. But if I zoom in a lot, I'm not really satisfied at all that I'm able to find a spot along this line where I am meeting these horizontal lines that extend and vertical lines that extend to the x and the y axis. So I do know that the slope is decreasing, and if I was going to try and come up with an estimate, I would say, let's see, this is just slightly below right here, and this is just slightly below right here. So considering that they're both slightly below, and they look like they're the same distance slightly below, I might say that this is, and as I'm going slightly below that, that this is my change in x and my change in y. So I do note that I am going, in this case, I'm going down 2 units. The length of that segment is 2 units long. And I'm moving to the right 1, 2, 3, 4, 5 units. So I would say the slope of this appears to be -2/5. But again, it's not, it's kind of well, if I look, I can see this same point right here looks like it's hitting in the same way. So, and that would be down to over 1, 2, 3, 4, 5. So probably a pretty good estimate, down to over 5. But I think we can see that there might be some limitations with finding the slope just based on a graph and drawing a slope triangles. It's definitely a good place to start if you can, but it may have some limitations. I do want to point out, and this is me just telling you, when I look at these lines here, there's 4 lines here. One of them is kind of a little bit hidden. But when I look at line A, it's very clear that A has a negative slope. It's decreasing. It's also clear, and let me color code this. I'll say that negative is it's going down. It's red. B is also has a negative slope. It's decreasing. C, on the other hand, appears to have a positive slope. It's going up. And in both cases, it's as I'm reading from left to right. So as I look at these graphs and I move from the left to the right, I can see in the case of A and B, I'm going down, and in the case of C, I'm going up. D, however, it does have a slope, but its slope is not positive or negative, right? Line D has a slope that is equal to 0. So in fact, if you were to look at this, if I was to draw to pick 2 points on it, I could go ahead and do this from this point to this point. I could see that my change in x is 1, 2, 3 units, so delta x is 3 units, and my delta y is 0. Delta y is 0. And it turns out when I take my delta x and I divide it by, I'm sorry, my delta y, and I divide it by the delta x, I get 0 over 3, which turns out to equal 0. I will caution you, if you see a situation where you're dividing by 0, remember dividing by 0 is undefined, but in this case I'm not dividing by 0, I'm dividing by 3. 0 divided by 3 is 0, so line D does indeed have a slope. Its slope is equal to 0. And because of the homework set today, I want to make sure that this gets into your notes. So I want this definition. What is the line of best fit? So I'll read this to you. It says, a line of best fit is a straight line that represents, in general, data on a scatter plot. As shown in the diagram, we're going to make a diagram in a minute. This line does not need to touch any of the actual data points, nor does it need to go through the origin. The line of best fit is a model of two is a model of numerical 2 variable data that helps describe the data in order to make predictions for other data. So if I was to create a quick scatter plot here, I'm just going to pick a few points. I could say this is a point I have. Here's a data point. Here's a data point. Here's a data point. Now, in general, right, it feels like something's happening with this data, right? It feels like it's showing some increase over time, and uh, it's not the case that I'm looking at just random noise, right? Whatever situation was used to collect this data, there's clearly some relationship between the two variables x and y. And I don't know that it doesn't have to be a causal relationship, but we can say that these two variables seem to be moving in the same direction together. Now, if I wanted to create a line of best fit, now that I have those points all plotted, what I do is I'm just going to take a straight edge and just move it until I find a line that feels like it's kind of going through the data. Now, trust me, this does not seem mathematical at all. And later in the course, we will actually we'll actually talk about how to calculate a couple a couple lines of fit, one of them being the least square regression line. But once I'm satisfied that I've got a line that's kind of, I've got some points above, some points below, I just kind of sketch it. And like it says, the line of best fit does not need to necessarily go through any of the data points at all. It just kind of has to try to describe in general what the data is doing. Again, we'll have much better tools for doing this later, but for now I just want you to realize that this is what a line of best fit looks like, and you find them right now by just plotting your data and then kind of attempting to draw a line that goes through them. Now, one of the things I can notice is now that I've identified this line that I'm calling a line of best fit, I could, for example, identify a couple points like this point and perhaps this is not bad, and this point, it's a little off. But these 2 points look like they're fairly close to helping me figure out what a slope triangle is. So if I wanted to describe the rate of growth for this data, I might come in and say, well, it appears that I've got this delta y, right, and I've got this delta x, and it looks like the data is indeed increasing, right? We can tell that because it has a positive slope, but we can find the slope, and then perhaps we could figure out the y-intercept. So that was a starred note for today. What is the line of best fit? Make sure you have those words and your own diagram. Okay, that is it for today. I've had a couple questions regarding, hey, Ms. Roberts, do we have to watch the videos and take the notes if we're in class? And the answer is no, right? If you're doing a distance day, the videos here just to help you instead of having you read through the book and do activities that really don't make sense if you're at home alone. I'm just trying to present the information in that book as in a concise way. So that's what you do if you're doing distance learning. If you're in the classroom, you don't need to watch the video and make sure you get the starred notes. I will say, however, though, that you know that I do lesson checks, and regardless if you're in class or you're away, you are responsible for doing lesson checks. So when you're looking at assignments, I make it really clear that it says it has a lesson check. So make sure you log in and you do those. And I will be dropping 2 lesson checks at the semester. So if for some reason you do miss one, it's not the end of the world. Just make sure, it would never be the end of the world. Just make sure that you're doing them and as we proceed through. All right, thanks very much. I look forward to seeing you in class again soon. This is Ms. Roberts. Goodbye.